Chapter 6 in Brown and LeMay deals primarily with quantum mechanics. So first of all, let me give my credits. Primarily for the lecture notes, it's going to be Brown and LeMay's chemistry and also Zumdahl's chemistry. Commentaries provided by myself. My name's down in the description of the video. Chapter 6 talks about things that are discovered by quantum mechanics. Schrodinger's equation. And so when we say that, what we mean is that we're taking the equation, which I put into the slides, which I'll show you at some point in just a few minutes, but it's a very complicated equation that you use in calculating different energy states in atoms and in molecules, and we're certainly not going to touch that as far as the math is concerned, but what we're going to look at is just what are some of the results of that, and that will allow us to be able to look at the periodic chart differently. So we'll understand it differently, and we'll see that there are actually 7 rows or periods, and each of those rows has a different number of subshells. And every time you come down one row in the chart, which technically they're called periods, then you're actually adding another subshell. So we'll learn more about that in just a few minutes. Let me skip through a few slides here. So we've talked about this and this. So talking about the basics of quantum mechanics, and I might just mention at this point, if you're interested in this, the lecture notes that I posted in your Houston Community College Canvas course are much more extensive than what I'm going to be doing here. So I went through these slides and pulled out or culled out a lot of slides, and there were several slides in there that dealt with how different types of rays or waves are produced, and I went through everything I could think of. But I pulled all those out for this set because it's not actually a part of the chapter. It's just stuff that I thought you might be interested in. So if you want to look at that, you'll have access to it in Canvas. If you just go to Canvas and go to assignments and scroll down till you get to the lecture notes and work problems, and you can find chapter 6 there and bring that up, and that will give you access to that information. So down at the bottom here, let me get my marker working. Here where it talks about how different sorts of light and waves are produced, we'll talk about that to some extent, but not as much as you would get if you went to the lecture notes. Okay, next slide. So what we're going to discover here is basically why these groups in the chart are the way they are. Now, when you first look at the chart, it probably doesn't occur to you that it's actually divided up into various parts. So before we go any further, let me just draw some lines here. So these first 2 columns here are one part of this chart, and that's why they're different from the things next to them over here on the right. So these first 2 columns are actually representing what's happening when you fill a certain subshell. And then that happens over and over again. So it happens in the first period, in the second period, in the third. And so we're going to find that we're going to have 7 periods in the atoms that we are familiar with on Earth. And that doesn't mean that there aren't more. I mean, you could, and some charts actually do come down to 8, 9, and 10, but it's just that we don't ever deal with those particular elements or atoms, so we don't really worry about them. So they have this one over to about 116 here, which that's about right. These down here at the bottom are almost all man-made. They typically don't last very long either, so they're not particularly useful. They're just of interest scientifically. And who knows, maybe someday somebody will discover a use for one of those. But anyway, and then over here on the right-hand side, and I think I'll probably stop at this point and move on, but these 6 last columns are in a group by themselves for a reason. And that's because they're also representing what happens when you fill another kind of a suborbital. I realize you don't understand what that means, but you will in just a few minutes. And then also the ones here in the middle that we've been calling the transition metals also, they're another suborbital. And then also the ones down at the bottom here, which we almost never talk about. These are also another suborbital. So you can basically divide the chart up into 4 parts. And this is completely independent from what we were talking about before, where we said, okay, the one way we can divide the chart, and this is not what we were just talking about, but you can also draw a line like that. And things above and to the right we call nonmetals, and to the left we call metals. And then the things that are kind of like in the light blue color in the middle, we call metalloids. But that's not what we're talking about here. All right, so let's go on, because I have a tendency to get bogged down. Let's move on. So light is kind of a loose term. So it actually might be more accurate to call it electromagnetic radiation, but we call it light, and that's the way it is. So but actually light, the stuff that we call light, is only one tiny part of the whole electromagnetic spectrum. It's one part of it. So what we call light is basically visible light. That's from about 400 nanometers of wavelength up to about 750 nanometers of wavelength. So, I mean, if you have a wave, like let's pretend that this is the baseline here, where I'm drawing this line, that black line, and then a wave, a typical sine wave it's called, you don't really need to know that, would look like that. And the distance from one peak to another peak is the wavelength, and the number of these wavelengths that goes by some certain point per second is called the frequency. And the thing that electromagnetic waves have in common is that for all of them, when you multiply their wavelength in meters times their frequency in cycles per second, and when you say cycles per second, that just means how many wavelengths go by every second. And the numbers are just astonishingly large. But anyway, when you multiply the wavelength in meters times cycles per second, you get the speed of light, which is 3 times 10 to the 8th meters per second. And that's true anywhere in the electromagnetic spectrum. So what's included in the electromagnetic spectrum? Well, you start on one end with gamma rays, and then what we call visible light is kind of like in the middle, and then on the other end, at the other extreme, would be things like things that have longer wavelengths, like radio waves. And then at the very end, you have the waves that go through your lines in your home or your apartment, which could be your home too. So like the electricity that goes through your circuits in your home is also electromagnetic radiation, believe it or not. So, but it's going at a very slow frequency. It's about 60 cycles per second. Whereas the gamma rays are at a very, very high frequency. So anyway, what they all have in common is that they have the same number that you get when you multiply their wavelength times their frequency. So what's included in that? Well, actually, it's probably going to be easier for you to see this if I go ahead and look at the chart. I don't know if that's on the next. Let's go to the next slide. Okay, so here again, we're talking about the basic definition of here is a wavelength. So it's the distance from one peak to the next peak. Amplitude, we're not going to worry too much about in this class, but it's the height from the baseline to the height of the peak here. It's called the amplitude. And then the frequency is the number of times that a wave goes by per second. Let's move to the next slide. All right, so here is the chart. This is a real simple one. So you see that when you're down at this end, the wavelengths are very short. 10 to the minus 12th meters. That's one, nanopicometer. And the frequencies are very high, like over 10 to the 20th cycles per second. If you can imagine a number that large, that's how many waves go by per second. Excuse me. Excuse me. And then as you move to the right on this one, and you can put these so that they're set up either way. It doesn't have to be this way, but if you, and the way this one is set up, if you move to the right, then your frequencies are going to decrease and your wavelengths are going to increase. But still, whenever you multiply anything on this scale times anything on this scale, you're going to get the same number. And that's going to be 3 times 10 to the 8th. But anyway, to go back to what we were saying, as you move to the right here, then you get into the X-ray territory, and then ultraviolet here. And then visible light, as I said, is kind of like right in the middle. And then as you keep going, you cross infrared and then microwaves, which are actually part of radio waves, and then radio waves. And then all the way over here, when you get to 60 cycles per second, which that's going to be like, it's going to be over here somewhere. Then you're at the kind of EM that goes through your wires in your home. Then that's called power engineering, because it runs the stuff like your refrigerator and all that. So microwaves here are considered to be part of the radio spectrum as well. It's just that they can be used for other things, like obvious other things. So, but also there is radio communication in the microwave region. So again, the thing that you need to remember from this mainly for right now is that if I pick any point on this top axis here, like right there where I'm drawing this little dot, then if I multiply that by this frequency below it, I'm going to get the speed of light every time. So that is an equation that we're going to use, and it's very important, and that is that the c, which is the speed of light, equals these equal signs are so hard to make, and then it equals the wavelength, which we abbreviate as lambda, times the frequency, which is abbreviated as nu. So this is the lowercase Greek letter for L, which is lambda, and that's the lowercase Greek letter for N, which is nu. And when you multiply, and this one stands for the wavelength, and this one stands for the frequency, and when you multiply them together, you get c, which is the speed of light. So that is 3 times 10 to the 8th meters per second. So you'll want to remember that number. And then I think we might, before we go on, I just want to point out that the wavelength of red light over on this side of the spectrum of visible light is going to be longer than the things down on this end, which are going to be violet. So ultraviolet, if you want to remember it this way, has a shorter wavelength than visible light, and infrared has a longer wavelength. Let's move on to the next slide. We'll talk about this more later. Here's another slide. This shows it in a little bit more detail, and it's flip-flopped. So what was on the right and the previous slide is now on the left. You can see what I was talking about. Here's your 60 hertz. That's the electricity going through your wires. And then there are some other things over here on the right that have been added in that are, I mean, the cosmic rays are not really rays. Cosmic rays are just things that are falling down to Earth from outer space. And gravity A waves is something I put in here, which you don't need to remember this. Some people theorize that there are 2 kinds of gravity waves. And the one that's marked here is the one that would be dealing with gravity at a very small scale, like within an atom, which most scientists would refer to that as the strong force. Some people think that it's actually an electromagnetic wave with a very, very high frequency. Let's go to the next slide. All right, so how are visible light, infrared light, and ultraviolet light produced? So it turns out, as we've talked about before, actually, that we talked about this in the context of Thomson's cathode ray experiment, right, where he pumped out all the air out of a vacuum, out of a glass tube, and put some kind of inert gas in it, like krypton or neon or argon, and then he turned on a potential between the ends of that glass tube so that electrons would fly off the negative terminal into the positive terminal. And we said at that time that when the electrons were going through these argon atoms, they would occasionally hit one of the argon atoms, and they would cause it to become excited. And what we mean by that is that, I mean, for right now, what we mainly mean is that the electrons can get moved up to higher states. So, for example, for argon, if you had an electron, let me find a place that isn't being used. So let's say you have an electron right there. And if it gets bumped by an electron that's going across that tube, it can cause that electron to become excited and move up to that state. And so, I mean, it has to be exactly the right amount of energy, but if it does get that amount of energy, it could move up to, let's say, n equals 6. So what we mean here by these n numbers is that that thing in the middle that I'm circling right now is the nucleus. And then electrons can exist in different wave functions which spread out at different levels around the atom. So, I mean, you could have one waveform that's like that, and that would be called n equals 1. So that would be like the first main shell. And then you could have n equals 2. And that's, so the numbers 1, 2, 3, 4, 5, 6 are referring to that. So when I say that it could get bumped up over here to n equals 6, what I mean is it could get bumped up if it has an integral amount of energy that's imparted to it. It could be bumped up all the way to n equals 6 up here, but it doesn't want to stay there. So it may typically only stay there for a few nanoseconds, and then it will drop back down. But the question is whether it will drop back down all the way back down to 1, or if it'll drop back down to 2, or if it'll drop back down to 3. All right, so here's the deal. If it drops all the way down to 1, it will emit light, because what's happening is this energy is a higher amount of energy than the energy down here anywhere. The further you go down towards the nucleus, the more negative the energy becomes. So in other words, what we're saying here is that this outer shell out here is higher in energy. It's higher in energy than these inner shells. In fact, every time you come down a shell, you're dropping in energy. And you'll want to remember that for reasons that we'll get back to in a little while. So when it drops, for example, from 6 out here all the way down to 5, 4, 3 to right there, let's see, is that 3? Yeah. So what's happening is it's going to have to give up energy because it's dropping to a lower energy state, and it gives off that energy in the form of light. Now, we've talked previously about how things can give off energy in the form of heat, but in this case it doesn't give it off in the form of heat. When it moves to a lower energy state, it gives off that extra energy in the form of light. So here's the deal. If it drops to n equals 3, the light that it gives off is going to be infrared. It's going to be in that range of the electromagnetic spectrum that is called infrared. That's if it drops to n equals 3. If it drops to n equals 2, it will produce visible light, and that's what we see around us. And then if it drops all the way down to n equals 1, it will produce ultraviolet light. So that's how those three are produced, and that's all listed here. Let's go to the next slide. All right, so here's our basic formula. We're going to have another one later, but for right now, the speed of light, which is c, equals the wavelength times the frequency. So we're going to use this one a lot in doing our work problems, and so this will be one of the things that you'll want to memorize, even though it'll probably be on the formula sheet. And you'll also want to remember that the speed of light, which is abbreviated as c, is 3 × 10⁸ meters per second. Okay, next slide. So here's a very simple problem. The light blue glow given off by mercury street lamps has a frequency of this much. What is the wavelength? So you'll just use your c equals lambda nu. And every time I have to do equals, it takes a long time and you can't ever read it. But anyway, so c equals lambda nu is the equation that we're going to use here. And we know c always. We always know c. And then in this case, they're giving us the nu. So that they're giving us right there is the nu. It's the frequency. So if we want to figure out what the wavelength is, we just divide both sides of this equation here by nu. And that will get rid of the nu on the right and put it under the c on the left. And that's what you're seeing here. So the wavelength will be the speed of light divided by the frequency. And we know what the speed of light is. So all we have to do is write the speed of light on the top and then transfer that 6.88 times 10 to the 14th seconds to the -1. That's also called hertz. So 1 hertz is the same thing as 1 over seconds, which is the same thing as seconds to the -1. So just take your calculator and type in 3e8 divided by 6.88 e14, and you get 4.36 e - 7. So that's your wavelength, and it's gonna put it out in meters. Okay, that's just because that's what the units will be. So these units have to be specifically in meters and in 1/2. And the speed of light obviously has to be in meters per second. Anyway, so the wavelength is actually going to be 4.36 e minus 7 meters. And that's your answer. Now, they asked for us to do it in nanometers, so you want to use your conversion factor where you have 10 to the 9th nanometers in 1 meter, and that's something we talked about in Chapter 1. So 1 nanometer is 10 to the minus 9th meters, so there would be 10 to the 9th nanometers in 1 meter. So if you multiply by your conversion factor, the meters here are going to cancel, and you're going to wind up with 436 nanometers. And remember, we said that visible light is between 400 and 750 nanometers, which you might want to just try to remember that. So, and notice here that this is light blue here, so that's telling us this is visible light. Next slide. Here I've put this in again to show you that this is the area where that problem that we just did would land us, right in there somewhere. Next slide. Okay, when you have a prism, which is like a crystal that has a certain shape to it, and if you shine sunlight through it, for example, then you will get reflected out of that a spectrum. So when you do a prism like we just said, then you get a continuous spectrum where you're going to see like a rainbow where you have all the colors in there. However, there's another kind of a spectrum called a line spectrum, and this is going to be different for different elements. So, in other words, if you shine light through different elements, you get different spectra. For example, and I had some examples in here, and I think I removed them for the purposes of this video. But, for example, hydrogen or sodium would give off a specific kind of a spectrum. And these are called emission spectra. When you take, if you do take organic, you'll talk about some different kinds of spectroscopy. And basically, this is not what you're going to be talking about. So this is called emission spectroscopy. That's why I put it in here, so you become familiar with that. When you take, if you do take organic, you'll be doing absorption spectroscopy mostly. Let's go to the next slide. So absorption spectroscopy, like you would do in organic chemistry, can be things like infrared spectroscopy or UV vis, and you'll possibly do experiments with that. Emission spectroscopy is what we were just talking about. Nuclear magnetic resonance, which you would also talk about in organic chemistry, involves both absorption and re-emission of electromagnetic radiation. So next slide. So, I do have still some in here. So here are some examples of emission spectra. This one on top is sodium, and it's just these two yellow lines right next to each other. So actually, if you were good at this and if you've done it a lot, then you would be able to just look at the spectrum and immediately see that's sodium. So that's a way that you can identify different substances. And then this is the way hydrogen looks. At the bottom here, this is hydrogen, and it has 4 lines. Actually, it has more than that. They're only showing the visible ones. So you'll notice there, at the right, you have a red line, and then kind of a turquoise over to the left, and then a light blue, and then a darker blue. There's, and then if you kept going to the left here, you would come into some more lines, but those are going to be in the ultraviolet region. Okay, so next slide. So what we'll do is we'll look at where those lines actually come from. We've already talked about this, so let's move on. I'll let you read this on your own. Let's move on. Okay, so when you're in an atom, and we're going to talk about the hydrogen atom mainly, but it could be any atom. I told you before that those n numbers represent wave functions, and so it turns out that those wave functions can only exist in certain places. For example, if you had your nucleus here, then you could, let's say, have a wave function here, and that would be n equals 1. And then you could have a wave function here, and that would be 2, and so forth. And then you could have 3, 4, 5, 6, and so forth. So that's 3, 4, and then I won't draw any more. What I want you to understand is that you can have these uh, wave functions. They can't be here in this region. They can't be there. They can't be here. They can't be here. They cannot. And they can't be here. They have to be in exactly there or there or there or there. And there's a reason for that, which I'll try to explain. I usually draw this on the board in a classroom situation, but there's a reason for that, which I'll get to in a second. But so it's important for you to understand this. So if you end up with a wave function that somehow gets out here, like an electron gets out here, it immediately is going to have to snap up here or down here back where it started from. So when an electron gets bumped to an excited state, it has to basically absorb the energy from an incoming ray, which will cause the wave function to immediately expand so that it becomes much larger, so it will just spring out here like this. And then once it gives up energy in the form of light, it will lose a certain part of this wave function, which will make the wave function in a smaller diameter, and it will snap back down to, let's say, 2, which will make it visible light. Okay, so, but they don't stay in these regions between these orbitals. And the reason is because whenever you have a wave, it has a wavelength. And so in order for that wave to continue to propagate itself, it has to match at the ends. So like just to try to draw this, whenever you have this wavelength, it's in this case, it's being bent into a circle. So for example, here, what I just drew, if the nucleus is in the middle here, these have to match up when they come around to the other side and rejoin the wave. They have to match exactly. And that can only happen if you have, like, for example, let's say 3 or 4 wavelengths. So it could happen here, and then if you added one more wavelength, then you could have, or 2 more or whatever, then you could have another possibility where it could meet there exactly. But it can't meet here in this region or this regime because the wavelengths won't overlap exactly. Then you could maybe add another 1 or 2 wavelengths and have another way that they could overlap exactly out here. So that would, let's just say that would be 3, and this one would be 2, and this one down here at the bottom would be 1. So that would be n equals 1, n equals 2, and n equals 3. But you can't have anything in between there. So this is different from our experience, because our experience is that if you have 2 different spots on a line, you can, move something in between them anywhere you want. So at the macroscopic level, we can do whatever we want. We can put something wherever we want. We can make a string as long as we want it to be. But you can't do that in an atom, or also it turns out in a molecule either, because of this thing right here. So this is called the quantum effect, and it's the basic reason, excuse me, why things at the atomic and molecular levels are quantized. In other words, they have to exist in multiples of 1. So, here we've got 1, here we've got 2, here we've got 3. So it has to either be 1, 2, or 3. It can't be 2.5. And for the reason that we mentioned before. Okay, so let's go on. All right, so electrons move around the nucleus in what we are going to call wave functions. They used to think that electrons went around the nucleus of an atom like planets go around the sun, but we know that isn't true now. The way that they actually go around is they basically exist all the way around in the entire circle simultaneously. And that isn't exactly true, but for all practical intents and purposes, it is. So, actually electrons are particles, but when they're in atoms, they kind of exist more like a standing wave. So even though it is a particle, it also has very strong wave characteristics. So you could actually say it's like a wave and a particle at the same time. So in one sense, you can think of it as an electron is going around the nucleus, but in another sense, and probably more accurately, you can think of it as a standing wave where it's basically present in a circle all the way around the nucleus. Okay, so next slide. All right, now here we have a picture of this in a different way. So the y-axis is energy. So the nucleus would be down here, and here is n equals 1. That's the very lowest level that's accessible for your electrons. And then as you move up, you get to n equals 2 here, and then 3, 4, 5, and then you go on out to infinity. So the way that they set this up is that they say that the energy all the way out here in infinity, or I'm sorry, at infinity, is 0. And then the closer you get to the nucleus, the lower the energy gets. It becomes more stable. So that means that electrons want to be as low as possible. So if they can get into n equals 1, they will, although there's not very much room there. So how would you be able to make it smaller if you're at 0 way out here? The answer is that they set it up so that the closer you get to the nucleus, the more negative the energy gets. So I think for hydrogen, when you get all the way down to n equals 1, if I'm remembering correctly from quantum mechanics, it's minus 13.6. Here would be the energy level. So as you move this way, the energy becomes less negative. And then once the electron leaves the atom completely, it's considered to have a 0 energy. So when it's just floating around in space. Here, for example, if you look right here, the blue arrow is dropping from 5 down to 2. So it's putting out visible light. Same thing for the green and the red arrows. They're all putting out visible light. So, and actually it turns out that these match up with 3 of the 4 lines that we saw in the emission spectrum for hydrogen in the visible range. So if you wanted to, you could also draw some more arrows here from hydrogen that come down to 1, but they just chose not to draw those. But they're there. All right, so we have some problems where we have to figure out what the wavelengths would be, excuse me, for these. So let's go on. Here's another picture of it. I'll let you stop it here. This picture actually does show the ultraviolet lines over here on the spectrum. Let's go on to the next slide. And next. And next. We've already seen this. So here is the first formula that we're going to look at very briefly. And the reason I'm not going to spend any time on this is because we're going to move to the more modern version of this. But it says that 1 over the wavelength of the light that's being produced when, for example, an electron, let's say it falls from 4 to 2, with a wavelength, or 1 over the wavelength of that light that's produced, can be calculated by multiplying what's called the Rydberg constant, which would be given to you on a test, times 1 over 2 squared minus 1 over n squared. So the 1 over 2 is written as 2 here because that is the level that the electron falls down to. So in visible light, or I'm sorry, for visible light, remember we said that it falls down to n equals 2, right? So that's where this 2 comes from. So if we wanted to do this for like ultraviolet light, we would just change the 2 out for a 1. And then the n obviously is going to be where it starts. So if it starts at 6 and drops to 2, then where that n is, you would just put in 6. And then that would allow you to find the wavelength. So let's just very briefly consider this and then we'll move on. If it were falling from 6 to 2, and that's what they told you in the problem statement, you just put 6 there for n. So you'd wind up with n squared would be 6 squared, so that's 36. 2 squared would be 4, so you'd have 1 over 4 minus 1 over 36. If you get these reversed, you're going to get a negative number when you do your subtraction. You'll know you did it wrong. So you have to kind of try to remember, although the formula is given to you. But the one that it falls down to is written on the left, and the one that it falls from is written on the right. So you would subtract 1 over 4 minus 1 over 36. Whenever you do problems involving reciprocals, I strongly recommend you write this stuff down as you go, because trying to do all this continuously in a calculator, you can almost always find some way to mess it up. So I would just do these things one at a time and write down each step. The Rydberg constant is given to you in either meters or nanometers, and then once you multiply the Rydberg constant here times whatever you get when you do 1 over 4 minus 1 over 36 in our example here, that's going to be 1 over the wavelength. So to get the wavelength, you have to flip it and take the reciprocal of that. All right, next slide. the reason I didn't want to spend a lot of time on that one is because there's another more modern version of that equation where you, instead of putting a 2 here, you put M, where you can now do anything. You can do, excuse me, visible light, ultraviolet light, or infrared light. So you can put in for M here 1 or 2 or 3. So, I mean, and then N would be still the same. It would be the level that the electron falls from. And then here you're also given your constant, your Rydberg constant, which this is the form we're probably going to need the most. It's 1.1 times 10 to the minus second nanometers. Excuse me, I'm sorry. To the minus 1, or in other words, this is 1 over nanometers, which that's actually what you need for this, because you're going to wind up with your answer as 1 over lambda. So let's go on. So I'm just reminding you that this is the spectrum on the bottom here for hydrogen. Let's move on. And then we've already seen this, so I'll let you look at this on your own. Let's move on. All right, so what color of light is emitted when an electron falls from 5 to 2? So let's go over to the next slide, because it's just easier for me to show you how to do this. So what we're going to do is we're going to put 5 right here, and we're going to put 2 right here. And because it's falling to n equals 2, we know that this light that it's producing is going to be visible light. So we should get something in the visible range if we did it right. So we're going to wind up here with 1 over 2 squared, which is 1 over 4. And here we're going to wind up with 1 over 5 squared, which is going to be 1 over 25. And then we're going to multiply that by the Rydberg constant here, which is about 0.011 nanometers to the minus 1. And then all of that will be divided into 1. Because what I did here was I actually rearranged this equation to make it easier, because this way we're actually solving for lambda rather than 1 over lambda. So I just rearranged the equation on the previous slide to get it this way. And then, so we just, for this, when you write it this way, you can just substitute in M and N and then just do your calculations. So I wound up here with 1 divided by the Rydberg constant times 1 over 4 minus 1 over 25. And I won't do the math here, but you should do that yourself, and you're going to get an answer here in nanometers, because that's the units that you have for your Rydberg constant. And most of the time, that's actually more useful to us to get it in nanometers, because if you get it in meters, it's just going to say times 10 to the minus 7th or whatever. Anyway, so do this on your own and see if you get the right answer. And then also, so the answer here should be 434 nanometers. So you should get 434. And then there was another problem where you are going to do the same thing, except you're going to put a 4 here for your N and then another one for 3. All right, so let's stop here for one moment. So I would go back through all of these from scratch. I would take a piece of paper, write down your formula. You can either write it the way it was on the previous slide, or you can write it down the way I have it here. I mean, this is actually easier. And then I would use n equals 5, n equals 4, and n equals 3. And by the way, that n that we're using here is not the same as the n that we were talking about earlier when we said n equals 1, n equals 2, where we were talking about the main levels of an electron. That's just a coincidence that they're using n here. It's actually unfortunate because it's confusing. Before we go on, actually it would have been easier to show you on the previous slide, but let's just think about this for a minute, because we're going to need to be able to do this for some of the problems. So if you're falling from 3 to 2, then that's going to be a small amount of energy change, because you're only dropping one level, as opposed to if you're dropping from 5 to 2, that's a lot of energy change. And when I say energy change, I'm referring to what I said previously, because those n levels correspond to more and more energy. The higher up you go, the more energy. So the farther you fall, the more energy. Now the point I want to make now, and then we'll come back to it later, is that energy is directly related to frequency, which means that if it's a lot of energy loss, it's also going to be a large frequency change. Okay, and because frequency and wavelength are like uh, the opposite. In other words, if you have a big frequency, you have a small wavelength. Then the smallest wavelength change would occur when you have the biggest frequency change. And the biggest frequency change will occur when you have the biggest energy change, which means that's going to happen when you fall a long ways. So like from 6 all the way down to 2 or 6 all the way down to 1. On the other hand, if you just fall a small distance like from 3 to 2, then your energy change is low, so that means your frequency is correspondingly low, which means your wavelength change would be high. In fact, that would be the longest wavelength line that would be produced would be when you fall the shortest distance. So let's just show that that's the case here. This is the longest wavelength here that we're getting out of these three answer choices. We have 656, 486, and 434. And it happened when we fell the shortest distance. Okay, next slide. And here I put this in again. Next slide. All right, so we're going to move on now to a different topic. The photoelectric effect refers to the fact that if you shine like a really bright flashlight on a piece of metal, if it's a certain kind of metal, electrons will fly off. And the reason they fly off is because what's happening is that the energy in the light is knocking them out of the atoms. Now, this will typically happen to things that are in the first column or group, the alkali metals, like, for example, sodium. So, for example, if you had a piece of sodium, a solid piece of sodium that's just elemental sodium, and you shine a light on it, if that light has enough of a frequency, it will start to knock electrons off of that sodium. Now, they'll float around in the air for a minute, and then they'll probably go right back on the sodium. Because things tend to not stay charged very long if they can help it. So, but the point is that you can do this. So what's happening is that I'm sorry, this room that I'm in right now is just loaded with allergens. Uh, if you shine a light on a piece of metal with the idea you want to knock some electrons off, you have to have a light that has enough frequency. And remember, I just said a moment ago that frequency and energy are very closely related. The higher the frequency, the higher the energy. So basically what you're doing is you're having to have a light that has a high enough frequency that it will be able to have enough energy to knock electrons out of atoms. It's easier to knock electrons out of things in the first column or group because they have one electron in their valence shell that they would just as soon get rid of, because then they become oriented in octet configuration, so they're happier. So if you shine a light on sodium or potassium metal, as long as that light has enough of a frequency or energy, then it will knock electrons off. But you couldn't, for example, shine infrared light on sodium and expect electrons to come off, because infrared light doesn't have enough of a frequency. So, in fact, a lot of visible light wouldn't either. It would probably have to be something over in a higher frequency range, like, for example, violet light might knock electrons off of sodium. It has to be something in the higher frequency range or the lower wavelength. Remember, those are synonymous. And then certainly if you get into the ultraviolet region, that's definitely going to knock them off if it's an alkali metal. If it's something in the second column or group, like the alkaline earth metals, like magnesium metal, then you would have to have a higher frequency because those electrons are held more tightly. So you would probably have to go into the ultraviolet range. I mean, either at least into the near ultraviolet or whatever, and maybe even to the far ultraviolet to get the same effect. So the reason for this is that in order to knock these electrons out of these atoms, you have to have enough energy to do it. And since the energy is related to the frequency, it's going to go by the frequency. So the higher the frequency, the more likely you're going to be able to knock electrons out. So something like a gamma ray or an X-ray is very high frequency, very high energy, therefore. And so they can ionize or knock electrons out of just about anything. So let's go ahead and go on down to the next slide. So this is just a picture that's showing you what I just said. So notice here, I wouldn't worry too much about this part at the top, but at the bottom, notice that if we start to increase the frequency as we go from left to right, and that means, for example, we might start all the way over here on the left with visible light, like let's just say something neutral like green. So let's just say that's green. And then we start to increase the frequency, so we go across the range until we get to violet over here, like here. And then we continue to increase the frequency, and let's say we get to ultraviolet. And then if you kept going, you'd get to X-rays and gamma rays. But once you reach a certain point, then that means you have enough energy that you're going to be able to go into these atoms and knock electrons out. And once you reach that point, it's there permanently. And the more you increase the frequency, it's not going to change anything because you already have enough energy to knock the electrons off. So it'll just stay the same. It'll just level off and stay the same from then on. The only difference between these two at the top here is that at the top, for the higher intensity light, it just means it's brighter than the one. It's the same frequency. In other words, it's the same color, but it's just that it's a higher intensity, so obviously it's going to knock out more electrons. But the thing that you should notice here is that there's a certain frequency below which you don't get any electrons knocked out because there's not enough energy in the rays to knock them out. Or in other words, we could say it another way by saying the frequency is too low. So for example, orange light might be in that category. So I've got a piece of sodium and it's sitting on a counter and I shine orange light on it and nothing happens. And not that you'd see the electrons anyway, but let's say you have some way to measure. Then the orange light, let's say nothing happens, but then I shine purple light on it and all of a sudden I'm getting electrons. The reason is because the purple light has a higher frequency. And if you want to look at that, look back at one of these, pause the video and then go back to one of the slides that has the electromagnetic spectrum on it. Next slide. So here we're explaining what the photoelectric effect is, so I'm going to go ahead and move on. Next slide. So here's our second equation. I'm not going to read the whole slide here, but I am going to point out this equation right here. It's very important. So even though, again, it's going to be on your formula sheet, I would memorize it. And it is just showing you the relationship I've been alluding to between energy and frequency. The higher the frequency, the higher the energy. I mean, you could write this as a proportion. You could write this that E is proportional to the frequency, and the constant of proportionality would be H, which is Planck's constant. So this is just a constant. It's just a number like pi. Okay, so H would be given to you on your formula sheet, so don't freak out about it. Just from memory, I think it's 6.64 times 10 to the minus 34 joule seconds. But I would have to look it up. Excuse me, I'm sorry. But anyway, it's just a number. So in other words, what it's saying is if you want to know what the energy is, then you would take the frequency of that light, which you would just either be given or you would look it up, and you would multiply it by that number that I said. And that will give you the energy, and it will give you the energy in joules, Joules. Remember, we usually want to get energies in joules. And we also want to get work units in joules because work and energy are interchangeable in some sense. They're like two different forms of the same thing. So anyway, so to get energy in joules, you would multiply Planck's constant times the frequency. And you can look up the frequencies on that EM spectrum. Next slide. So alkali metals, things in the first column, they're going to give up their electrons more readily. So you don't have to have a particularly high frequency of light to get them to lose their electrons. Just visible light will do it. Other metals not in the first column, so second column and then over to the right, you have to be over in the ultraviolet light range. And then nonmetals typically don't want to lose their electrons, so you really have to get a high frequency in order for that to be enough to knock electrons out of a nonmetal. So that means you're going to have to be all the way over in far ultraviolet or higher. Next slide. All right, so in 1914, Niels Bohr proposed a planetary model of the hydrogen atom, which was wrong It was a good start, though, so let's go to the next slide. And we've already talked about this, so let's go to the next slide. So the way that he pictured this was that there were orbits that these electrons that were negatively charged went around when they were going around the nucleus. And that's wrong. Actually, this word right here and this word right here, this should actually be written as orbitals. I'm not sure here if they're referring to his theory at that time or if they're referring to the way we look at this now. But if it's referring to the way we look at this now, we don't call them orbits. We call them orbitals or wave functions. Okay, next slide. And then this is in here, which I really kind of like get a little frustrated having to teach this because it's not something we're ever going to use. But they insist on always putting it in, and then it seems that they always ask a question on the final about this. So de Broglie in 1924 suggested that if light can behave in some respects like matter, perhaps matter can behave in some respects like light. Well, we know that's true. I mean, matter can be converted into energy and vice versa. And so what that means is that whenever something's flying around, it's going to have a wavelength. Like when a pitcher in Major League Baseball throws a pitch, the ball will actually have a wavelength, but it's so tiny you can't measure it. And so when you get down to the atomic scale, what happens is that things that are really small, like electrons or really even atoms in some cases, when they're moving around, they'll have a wavelength because they're so light. In fact, when you get down to the electronic level, the electron is so tiny that it has as much of a wave character as it does a particle character. So you can think of electrons as being wave particles. And then certainly things that are even lower down in the mass scale than electrons, like for example neutrinos, are even more that way. So the neutrinos and even electrons have really large wavelengths. So just to go ahead and get this out of the way, de Broglie suggested that the wavelength of some particle at the macroscopic scale could be calculated by taking the Planck's constant we talked about before, which is down here, 6.63 times 10 to the minus 34 joules per second, divided by the mass of like the baseball times the baseball's velocity. So you can see that if you're dealing with something where you've got like a, I don't know, certain amount of kilogram baseball times a certain amount of meters per second, and you divide Planck's constant by that, you're going to get a wavelength that's so tiny. I mean, so incredibly, like 10 to the minus 32 or 10 to the minus 33 meters. There's no way that it would be significant. So if I were you, I would at least look this over and be familiar with it. We're not going to spend any time on it because it's never going to come up. So let's go to the next slide. Okay, on the other hand, these things will come up. So we have a few definitions that we need to look at. So Schrodinger here is the one that proposed the quantum mechanical model of the atom, which we're basically still kind of following that today, where it focuses on the fact that electrons also behave as waves, which is why we call these electronic orbitals wave functions. So you can, again, if you want, you can think of this as being a situation where you've got an electron that's like a wave or a standing wave that's just in a circle, and it's continuously present all the way around the circle around the nucleus. So he's the one that proposed the quantum mechanical model of the atom that's based on Schrodinger's equation, which we'll look at in a little while. And then in 1927, the following year, Heisenberg said, and this is something you'll have to know because there will be questions on the test about this. He said that if you have an electron, because it's so tiny, that you cannot simultaneously know where it is and how fast it's going. Or to put it another way, you can't simultaneously know where it is and what its momentum is. And that's something you'll need to know as typically a multiple choice question, and that would be that's called the Heisenberg uncertainty principle. Now, it's actually not usually written that way. Let's go to the next slide. Oops, it went right past it. Okay, so anyway, it's usually not written that way. So what's happening here is sometimes this thing screws up. and it doesn't move to the next slide when I click it, and then I keep clicking it to get it to go, and then it suddenly wakes up and says, oh, I'm supposed to go. It's just, typical Microsoft crap. But anyway, so this is the equation that we've been talking about down here at the bottom, the time-dependent Schrodinger equation. So if you take quantum mechanics at some point, either in chemistry or physics, this is what you would use, where you're taking the wave equation and solving it to find where the electron is. So to go back to where we got cut off, again, thanks to Microsoft. I mean, I use Microsoft all the time, and I'm appreciative of it and all that it does, but they just could make it where it isn't such a pain in the butt to have to use things like PowerPoint and Word. They have all these little things in them, and Excel is that way to some extent, but they put things in it that just, it's like it makes it harder to use it than if they would just leave it alone. But anyway, so to go back to what we were talking about, the Heisenberg uncertainty principle is usually not written the way that we said it before. It's usually written in a form where they'll say that the lowest that you can know both the probability of where something's going to be and its momentum at the same time, it's usually written as like delta x times delta p, and that has to be less than a certain, or actually it has to be greater than a certain number. And that number involves Planck's constant and pi. So you'll have that anyway in your lecture notes, so just take a look at that. Be sure you're familiar with it. It's not hard to recognize. Okay, let's go to the next slide. So a wave function is the way that we designate the way these electrons go around nuclei. So instead of calling it like an orbital or an orbit, we call it a wave function. And it's abbreviated by this Greek letter that you're probably not familiar with. It's the Greek letter psi psi, which is a letter that we don't actually have in our alphabet. And so whenever you take psi squared d psi, you're talking about the probability of finding the wave function at a certain place. And if you want to know the overall probability of finding the wave function in an area, you would take the integral of that overall space, which we're not going to worry about that because it's beyond the scope of this class. So let's go to the next slide. All right, so what we are worried about is the way that we can interpret this. So let's interpret the Schrodinger equation that we looked at a few slides back and figure out what it tells us about the way atoms are constructed. So let's go ahead and move on. So I'm going to show you the next 2 or 3 slides here very quickly. This is just showing you a chart of if you start at the nucleus and work out, then if you take every little piece of space out here and determine what is the probability there's going to be electron density there, this is what you're going to get. So it's just like an asymptotic curve that is going to approach the x-axis. So this is just like, what is the density likely to be if I move a certain distance out? Now the next slide, or maybe the second slide following, is going to show you something that's a little bit different, where it's actually going to take a thin shell at one distance from the nucleus. And it's going to say, okay, if I take the volume of that shell times its probability there's going to be an electron in there, what will I get? And it's going to give us not this kind of a shape, it'll give us a different answer. Because what's happening is when you're close to the nucleus, even though there's a very strong possibility that you're going to find an electron there, it's also true that that volume is going to be lower. So when you start off at the nucleus, the product of the little tiny volume of that little tiny circle times the density is going to be low, and then it's going to come up to a certain point, level off, and then drop back down. So let's look at that next. And so here it is. And so it turns out that there's a certain distance which is referred to as R max, and that's actually going to be the distance from the nucleus where you're most likely to find the first electron in that atom. Okay, next slide. So the principal quantum number is the number we've been talking about in the past, where we've said that there's going to be a first main shell and a second main shell and so forth. So we said that we were going to call it n equals 1, n equals 2, and n equals 3, and so forth. So the higher the number of the n is, then the farther you are away from the nucleus. That means that also Some other things are going to happen, but we're going to talk about those later, so let's go ahead and move on. So the next thing that we're going to talk about is angular momentum quantum number, which is a big word that you don't really need to worry about it right now. Just worry about the fact that we have another quantum number, and it's called L. So the first one was called what? N, and that's just the main quantum number. And the second number is called L, and it is referring to the angular momentum, or some books call it azimuthal. And so we don't really need to worry too much about the name other than just to be able to remember what it refers to. But what we really are going to call this in our course is the subshell. And there are basically, for our purposes, there are basically going to be 4 of these: the S, the P, the D, and the F. And they also have numbers that are assigned to them because we're doing something that we're going to call quantum numbers. So in other words, for an atom, like let's say a hydrogen atom, but it could be any atom or molecule, we're going to assign a set of 4 numbers to that electron. And we're going to realize later that no 2 electrons in the same atom can have the same 4 quantum numbers. And that's kind of the whole point of this, is we have to have 4 different numbers to describe the electrons in order to get to the point where we can say that there's no 2 electrons in the same atom that have the same 4 quantum numbers. And that way we can give every electron in any atom a set of quantum numbers that will designate that specific electron. So the first quantum number, so there's 4 of them, and the first one is easy. It's just the N number. So it's just the main shell number. Are we in the first main shell, or have we bumped up to the second main shell, or the third main shell? So that is called the N number. The second one is the one that we're looking at right now, and it's called either angular momentum or azimuthal. And Brown and LeMay, I think, calls it azimuthal. So you'll have to just make sure that you can recognize both of those. So that refers to what the subshell is. And the subshell is like a shell within that main shell. And every time you come out to a new orbital, like for example, if you go from n equals 1 to n equals 2, then you're going to add one more subshell every time you do that. So when you're in the most inner level or wave function, n equals 1, you can have only one subshell. Now try to follow what I'm getting ready to say because it's important. You can only have one subshell for n equals 1, and that's called the S subshell, and it's spherical. So let me try to draw this a little bit. So there's the nucleus, and then here is the n equals 1 main level, and it can only have one subshell. So it only is one subshell. So it's the S subshell, which is a sphere, just by coincidence. So, well, not a coincidence, but anyway, it's a sphere. And so it's going to look like that. And that's all you're going to have for n equals 1. And that's all you can have because it's not big enough to accommodate anything more than that. Okay, now let me try to draw 2, and that's as far as I'm going to go because it's so hard to do this. But let's come out here and say, now this is n equals 2, okay? That when I say that, what I mean is that we're now in the second main subshell. Well, it will also have the same, shell. So n equals 2 here, let me write a little 2. N equals 2 will also have an S subshell, and it will also be spherical like the one below it. And also 3 will also have an S, 4 will have an S. In other words, as far out as you go away from the nucleus, every time you have a new shell, you're going to have an S subshell for every one of them. But it turns out, so you'll have like a sphere here. I'm trying to like make it into a sphere kind of, so you can kind of see that this is not a circle, it's a sphere. I'm not a real great artist anyway, and then this marker doesn't help. Anyway, but in addition to that, when you get out to n equals 2, so this is n equals 2, you can have another subshell called the P subshell. And I'm going to try to draw it. I'll try to draw part of it. Okay, so let me just draw one part of it. There's actually 3 of these things that I'm drawing right now. So let's call this PZ. And it's just a thing that looks like a set of dumbbells, kind of, where you've got one thing that's sticking up, straight up in the air, and the other thing sticking straight down. So This would be the one of what would eventually be 3 P's. So you'd have one sticking straight up and down, you'd have one going left and right, and then you'd have another one that's really hard to draw going into the screen and then coming out of the screen here. So you could call this one X if you wanted to, and then you could call this one Z if you wanted to, and you could call the one that's going in and out of the plane Y. But the bottom line is you have 3 of these. Okay, so the deal is this. For one inside here, this one way in here, right there, you can only have the S, so you would only have one S. Then when you come to 2 out here, so this is 2, you can have 2S, which I tried to draw here, but you can also have another one, because every time we come out one more N number, we add one more subshell. And that one is the P, and it's shaped differently. It's shaped like 3 dumbbells, like one going up and down, one going left and right, and one going in and out. So they're all at right angles to each other, okay? So I would refer to these as the 2 that are going left to right, I would call PX. And be careful here because it's 2 lobes, but it's just called one thing. And 2 electrons can go in that subshell. That's an orbital. So the px orbital here that I drew would be one subshell, one orbital, and it can accommodate 2 electrons. But you shouldn't think of it as like, okay, one electron's going to be on the right and one's on the left. I mean, you can think of it that way if you want, but when we get to the next one, it'll get more confusing. So just think of it this way. Think of it that one orbital has 2 lobes, one on the right, one on the left, and that whole orbital, both parts of it can accommodate 2 electrons. You see what I'm saying? Because we're going to find later that it'll become more confusing if you try to match the number of lobes to the orbitals to the number of electrons. You could do the same thing here for the one that's going up and down. So the whole thing here, the up part of it and the down part of it, is one suborbital. I'm calling it the PZ suborbital, and it can accommodate 2 electrons. So it could either have no electrons in it, or it could have 1, or it could have 2. Now, before we go on, let me just say a couple of things. First of all, if we go out to 3, let's just draw part of it out here. So let's say way out here we get to 3. So here is n equals 3. What do you think is going to happen then? What are we going to have for subshells? So think about it for a moment. Well, we're always going to have S's. Everything from 1 up is going to have S. And then also for the P's, everything from 2 up will have a P. So the 3 will have an S, and the 3 will have a P. But then because we're now moving out to another N level, we're going to add another subshell, and that's going to be D. So once we get to 3, we would have S, which would be a sphere, and then we would have P, which would be the dumbbells, which would be bigger for the 3 level than for the 2 level, and then we're also going to have D. So the D subshell would only be present if you're at n equals 3 or higher. Now the S subshell will have 1 orbital because it's a sphere. So we can only accommodate what 1 orbital could accommodate, which would be 2 electrons. The P's, because there are 3 of those, remember there's one sticking straight up and one left and right and so forth, but each of those can accommodate 2 electrons. But you have 3, and I'm not sure why I drew that line, but you would have 3 orbitals for P. And then when you get out to the 3rd main level, n equals 3, the D, there are 5 of those. And that isn't supposed to be D to the 5th. It's just, I'm writing that there are 5 parts or orbitals for D, each of which, again, can accommodate 2 electrons. And then if you want to keep going, because we're almost finished anyway, let's just do the next one and we'll be done. If you want to keep going one more, the next one for n equals 4 and above would be F, and it would have 7 orbitals, and each of those can accommodate 2 electrons. So you have a total of 14 electrons in F that can be accommodated. Now, because we're trying to make these all into numbers, we're going to assign a number to each of these. So instead of, we'll call these, like, for example, 3D or 4F or whatever. But if we wanted to write them, if we were asked to write them as numbers, the number that was assigned to S's is 0, and the number that was assigned to P's is 1, D's are 2, and F is 3. And that's as far as we need to go. Now, people have played around with G and H, which would be the next two, but because we really don't need those for the chart that we use, we're just going to forget about them. Just be aware that they're there, but we're not going to use them. So, in other words, what we're saying here is that this set of numbers right here, the 0, 1, 2, and 3, we're going to call that the second quantum number. So the first quantum number would be the n number. The second quantum number would be this number, which is usually called the L number. And that is the azimuthal or the angular momentum number. And we won't usually call it by its number. We'll usually call it either S, P, D, or F because it's so much easier for you to visualize those. But just be aware that each one of those S, P, D, and F things have a number associated with it. All right. Before we go on now, well, no, let's just go on. It's easier if you look at the slide. So we just mentioned this. So if the L number is 0, we said that 0 corresponds to S. And if you want, you can try to remember spherical S. P, if you want to try to remember peanut, even though it doesn't look exactly like a peanut. Some peanuts might look kind of like it. It really looks more like a dumbbell, but dumbbell starts with D, so it doesn't match. But anyway, and then D's are different, and I'll show you a picture of those in a moment. So that would correspond to L equals 2. And this is L over here, not 1. So that is the letter L. And then L equals 3 corresponds to an F suborbital. So you would only have this one right here from 1 on. Well, and that I shouldn't say only because that's for all of them. You would only have this one for n equals 2 and above. So 3, 4, 5, and 6. You would only have this one when you're at n equals 3 and above, and you will only have this one when you're at n equals 4 and above. So if you didn't catch what I just said, just back it up to the previous slide or two, and we talked about it there. Next slide. Okay, the third quantum number is just a placeholder. And to explain that, let me go back. I can't get back, but remember, let me just try to sketch it real quick, because I think it's going to be easier for you to understand this. Instead of looking at all those numbers down there at the bottom of the slide, I think it's going to be easier for you to see this if I just draw you a picture. So remember when we got to n equals 2, we said that a hydrogen or any other atom can have p suborbitals, which I kind of tried to draw like this. So this is supposed to be going into the plane of the screen. And then this one would be coming out. And why don't we like shade this one a little bit so we can kind of tell the difference. So the one that I'm shading and then the one that's dotted on the other side is going to be the one that's going in and out of the plane of the screen. So, I mean, if you want, we can call that Y, just so we can keep track of these things. We can call this one X, and we can call the ones going straight up and down Z. All right, so that's P. There are 3 of them. And notice every time we move out to a new n level, like if we move from 1 to 2 or 2 to 3, then the thing that we're going to add in as far as a new subshell is concerned, we'll have 2 more like orbitals available. So what I mean by that is for S, we only had 1 orbital. For P, we had 3. For D, we're going to see that we have 5, and we'll see a picture of that in a moment. And then for F, we're going to have 7, and then we're stopping there. So the rule is every time you move out 1 n level, you're adding a new subshell, at least to a certain point where we stop, but which means you're adding 2 more orbitals, or suborbitals, if you want to call them that, each of which can contain 2 more electrons. So if we want to just back up for a moment, the S suborbital can hold 2 electrons. The P's total, like if all 3 of these here can hold 2 each, but there's 3 of them, so that's a total of 6. So S's can hold 2, P's can hold 6, D's can hold 10 because there's 5 of them, and F's can hold 14 because there's 7 of them, 2 each. And we're going to discover as we look at the chart that those numbers I just mentioned, the 2, 6, 10, and 14, correspond to the number of columns in the chart in various locations. So we'll come back to that. Remember, we circled those 4 different regions on the chart at the very beginning. Okay, so let's go ahead and move on. But so what I was going to say about this is that for the X and the Y and the Z here, each of those can hold 2 electrons. And so we have 3 orbitals here. And so it's easier for us to see it if I call it PX, PY, and PZ, or at least it's easier for me. But in keeping with our goal here of assigning numbers to all these things, what they actually do is they assign numbers to these instead of calling them X, Y, and Z. But they do call them that also, in fact, most of the time. But just so that we can actually write it in number form, they assign numbers. And so these numbers that we're talking about right now are called the magnetic quantum number, and they just correspond to the X, Y, and Z here, but they're just numbers. So just as we assign numbers to S, P, D, and F, we're going to do the same thing for the X, Y, and Z here. So, and I'm not sure even which one corresponds to which one, but let's just say that's the -1, that's the 0, and that's the +1. So you can see that these numbers that I just said, the -1, the +1, and the 0, they're just placeholders. They're just numbers that we're putting in there to take up the place for that particular orbital. Nevertheless, that is the third main quantum number. So this is quantum number 3, which let me just write that here. So that's 3. So the first one is the N number. The second one is the subshell, or the L number. And the third one here is called the magnetic quantum number, and it's abbreviated as M sub L. The M stands for magnetic, and the L refers back to the angular momentum number that we talked about before. All right, let's move on. So here is all of the stuff that we just said, which I'm going to let you stop if you want here and look at this, because I'm already actually almost out of time and we still have almost half of this to do. So let's move on. So let's do this example. Identify the possible values for each of the 3 quantum numbers for P. And the answer is going to be, for the N number, it's going to be 4. It has to be 4. For the L number, it's going to have to be 1 because P corresponds to 1. And so there are 3 different possible ways you can write the M sub L, which is the one that we just looked at, which it's hard for me to make M's. So the M sub L could either be one of the 3 numbers that we just mentioned. It's either going to be -1, 0, or +1. So let's quickly move on. And here are the answers over here on the right. So it could either be, if you're going to write them in sets for each electron, you could write 4, 1, -1, or 4, 1, 0, or 4, 1, 1. So those would be the 3 quantum numbers. Next slide. And then here's another exercise. For the principal quantum number level, n equals 3, determine the number of allowed subshells. All right, so you could have S, P, or D. S is everything n equals 1 and above, P for everything n equals 2 and above, and D for everything that's 3 and above. So you could have any of those. You can't have F. You cannot. So you could have S, P, or D. And they're actually listed here. So these are the ones that you could have, but we're supposed to give the numbers. So remember, S was 0, P is 1, and D is 2. Next slide. And it's not going, and I don't really want to click it again, but I guess I'm going to have to. Next. Okay, so hopefully you saw the answer. If you didn't, you can go back and just pause it there. So what we're going to do now is we're going to divide the chart back up into the 4 regions that we mentioned before. And notice how many columns each one of these regions has. Let's see if we can put this together in our minds. So there's the second region. Here's the third one, which I'm kind of trying to make it so they don't overlap. And here's the fourth one. So if we counted the number of columns, not the rows, the columns, we have 2 columns here, 1, 2, and we have 6 here, and we have 10 here. Is this starting to ring any bells? And then we have 14 here. So if we consider that every one of the orbitals has 2 electrons that can potentially go into it, then we're talking about 1 orbital here, 3 orbitals here, 5 orbitals here, and 7 orbitals down here. So this is going to be when we fill the F's down here at the bottom, which we won't do much work in this area in this class, but anyway. So up here is going to be when we fill the S subshells. Here is where we fill the P subshells. Remember there was a PX, PY, and PZ. And then here is where we fill the D subshells. So we haven't seen a picture of that yet, but we will. But for D's, we have 5 possible subshells, and they're kind of oriented kind of like the P's, but with a couple of extra things thrown in there. But each of those can accommodate 2 electrons. So there's a total of 10 electrons you can accommodate. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's where those 10 columns come from. So when you move from for example, from this row, which it didn't mark, so from that row to that row, or actually it's better periods, from that period to that period, then you're just changing the size of the atom. Basically, it will have more protons and it'll have more electrons, and it'll be bigger. But the properties are going to be very similar. So what you're doing is, for example, here, this is D. The first D row here will be 3D. And you'll notice here, maybe if I have time, I'll come back to this, but this would actually be the 3D row. And this would actually be the 4D row. So if you're sharp, you'll notice that this is not matching what's over here. And the reason is because they moved the 3D row down from there where it theoretically should be. They moved it down. And the reason they did that is because that's the way that these electrons actually fill in real atoms in real life. So they put them where they would be energetically speaking. So in order to make it real, they had to move it down. All right, so just to review this very quickly, the 2 columns on the left are representing when you're filling S subshells. And the further down you come in the chart, it just means you're at a higher N level, and you're now filling, for example, here you're filling N equals 5's S subshell. And here you're filling N equals 6's S subshell. So that would be cesium with 1 electron or barium with 2. Same thing over here on the right-hand side. These are the P electrons filling. And we have 6 of those because there are 3 P orbitals instead of just 1. And then for the D's, we have 5. Let's go to the next slide now. So for L equals to determine the magnetic numbers and the number of orbitals, all you have to do is look at this number and take everything between +2 and -2. Or you can think about it in the way that we've thought about it up to this point. If you're at L equals 2, can you remember the letter that we associate with that subshell? So it's S, P, D. So this is going to be D, right? D has 5 orbitals. So we already know the answer to that. It's 5. And the numbers are going to be, as I said, anything between 2 and -2. So try to keep this in your mind. These M sub L numbers are just placeholders. We have 5 orbitals, so let's just draw. I mean, this isn't really the way they are, but just like one like that kind of, and then one that kind of goes this way and one that kind of goes this way. I think that's 5. And we'll see a better picture of that in a moment. But there are 5D suborbitals. So you could call them, for example, X, Y, Z, A, B, if you wanted to, and it'd be easier to see. But to put numbers on them, we have to put, like, one of them has to be -2. And then, so let's just do everything between 2 and -2 to make it easier. So 1 would be -2. We need 5 total. 1 would be -1. 1 would be 0. 1 would be 1. And so forth. So this set of numbers would represent the 5 M sub L are magnetic numbers for L equals 2. Let's go to the next slide quickly. And it didn't go, so I'm going to click it again. It may go to next. Next. Okay, there's the answer. Next. The number of electrons here it can accommodate would be 10. We have 5 orbitals, each of which can accommodate 2 electrons. You've got to remember that. You can only have a maximum of 2 electrons in any orbital. All right, let's go ahead and move on. I think we're going to get to some stuff that can go more quickly. So here, let's quickly look at some pictures, and I'm going to go through these kind of fast because you can just pause these if you want to look at them. So, for example, this is 1s, just a small sphere, and then it's around the nucleus, and then here is 2s, where the blue thing is the 2s and the red thing is the 1s. And then here, that's the 1s, here's the 2s, and here's the 3s. So every time you move out to a new n level, you just add another sphere. Next slide. Excuse me. And this is just another way of looking at the same thing we just looked at. Next slide. All right, here are the way the p orbitals look. So here we could call this px. It's easier to see that way. This would be py. So, or in other words, this would be py here, which is shown here. And then pz would be the one that sticks straight up and down. How many do we have here? 3. So each of those can accommodate 2 electrons, so that's a total of 6 electrons. Next slide. And then the next slide. Next. So the D's, that's not one of the D's, that's an F. So the D's look like this. So these are between the X and Y axis, the Y and the Z axis, and the X and the Z axis. And then there's one that kind of goes straight up and down the Z axis. And then there's another one that actually goes right on the X-Y axis. But the main point here is there are 5, which is 2 more than we had for P's, which was 3. So 3 plus 2 is 5. When we get to the F's, we'll have 5 plus 2, which is 7. And we're not even going to look at the F pictures because they're just so complicated. I mean, there's one of them, but we're not going to even worry about the F's, okay? And plus, we're not going to use them that much because it's the lanthanides and the actinides. So anyway, but here are the 5, everything except that. So these other 5 pictures are showing you the 5 different kinds of d orbitals. And again, each of these can hold 2 electrons. And that's why I told you not to try to match these lobes with numbers of electrons. Because if you did that here, for example, it would look like you'd have 4 electrons that could go in there. And you can't. So don't let that confuse you. You can only have 2 electrons in there. In the whole thing. In both of these, or all 4 of these lobes, you can only have 2 electrons. Next slide. And here's a better picture of the D's. And then next slide. Here's a picture of all of this stuff kind of put together. And for the sake of time, let's move on. And then the 4th quantum number, if you're wondering, is just the electronic spin. Electrons have a little bit of a magnetic field, and that produces a spin number. And so the way that they do this 4th number is they just say that the spin is either going to be oriented up or down. And we don't have time to go into that, and it probably wouldn't be that beneficial anyway. So just remember the 4th quantum number is either spin up if the electron's pointing up, or spin down if it's pointing down. And of course, as always, we have to assign a number to that. So whenever it's spin up, we call it, actually this is backwards, but anyway, one of them is going to be plus 1/2, and one's going to be minus 1/2, and it doesn't really make any difference which way you do it. Excuse me. So the 4th number will always either be plus 1/2 or minus 1/2. Okay, so, and that's it for the quantum numbers. Let's go on. All right, and then very briefly, this slide is just showing us the reason for the chart being the way. So when you actually fill the electronic shells, when you get to the 4 S's, it turns out that their energy level is lower than the 3D electrons. In other words, they're less stable. So as you fill electrons in an atom, you put more protons, so you need to put more electrons, right? But as you do this, the electrons are going to go into the lowest available orbitals. And it turns out that the 4s's are lower in energy than the 3d's. And this is for most atoms. So for most atoms, the 4s's are going to fill before the 3d's do. And that's the reason that the 4s's are written the way they are in the chart. In other words, we go through 3 whole rows or periods in the chart before we start sticking the d's in, even though, as I mentioned before, they actually should start in the 3rd row. But they don't, because the electron orbitals don't fill in the 3d's until after the 4s's. So they write it in the chart the way it actually fills. So therefore they write where the 4s elements, whatever they are, the first 2 elements in that row will be the 4s elements, followed by the 3d's. So it puts everything off by 1 row. Everything in the transition metal rows, everything is 1 row below where it should be, hypothetically. And then, I mean, it's less important, and we're not really going to worry about it that much, but this also happens for the F. So F's actually turn out to fill 2 rows below where they should be in the chart. So when you get to the 4th row, you should also have the F's there. And you don't, because they don't fill that way. So, I mean, again, we won't really need to worry that much about the F's, but just in case you're interested, for the F's, they're going to wind up 2 rows below where they should be theoretically. And they're not in the chart anyway, they're actually at the bottom. So, but if you look in the chart after the 2nd column down towards the bottom of the chart, you'll see where they left a little space there and they put an arrow and they say this is where the lanthanides would go. So, but that is also off because they actually should go 2 rows above that. So they should start in the 4th row. Let's move on. So this is basically what I just said verbally, so let's move on. So here's the chart. So you can see here that we start off here, we have the S's here and the P's here, and there they are. But when we get to the 3rd row, we should have the D's right there. And I mentioned this before. And they're not there. And the reason is because when these electronic shells fill, they'll fill potassium and calcium first because they're lower in energy than scandium and titanium and vanadium and so forth. So they put them in the chart the way they really fill in terms of their electronic energies. So to do it correctly, they have to put this first row of D's down here where they actually should be in terms of real life, as opposed to putting them here where you would think they would go. And then when you get to the 4th row here, you would also then theoretically have the F's over here. But if you put the F's there, they're going to make the chart incredibly wide. So they move them or migrate them down to the bottom here by themselves. But they should go here in the 4th row. Instead, they don't put them until you get all the way down to the 6th row. Okay, moving on. You can look at this on your own. This is just showing you how the electrons fill in different atoms. And what I would recommend that you do, since you're always going to have a chart available even on the exams, is if you want to know what the order of filling is, just look at the chart because it's done according to the order of filling. Next slide. All right, so a few definitions very quickly. Electronic configurations just mean how the orbitals are filled. And we're going to see some examples of that, which I'm going to have to let you do on your own because we're out of time already and we still have kind of a long ways to go. But the way that they're written would typically be like this. 1s2, 2s2, so or whatever. So it's hydrogen, helium, lithium, beryllium. So if you have a chart with you right now, why don't you pick it up and look at the first 4 elements. So hydrogen is in the 1s column, helium's in the 2s column, and then when you go to the 2nd row, you just start over again at the far left with lithium. And I'm doing this from memory, but lithium would be the 1s column, and then beryllium would be the 2s column. So for those first 4 elements, let's just do all 4 of them. Hydrogen would be designated, according to what we're talking about right here, as 1s1, because you have 1 electron in the 1s shell. So the first two columns represent the 1s, 2s, 3s, and so forth. So you're in the first row, so it's 1s, 1. And helium would be 1s2, even though it's out of place. So just mentally move helium back over next to hydrogen. Lithium would be 2s, 1, because you're in the second row now, so it's 2s, not 1s. And it has one electron in that. So it would be 2s1, and then beryllium would be 2s2. And then, let's see, boron is next, right? So if you skip all the way over to boron, that is now going to be 1s2, 2s2, 2p1, because now you have one electron in the 2p. So the configuration would be 1s2, 2s2, 2p1, and then carbon, I believe, is next. It's BCNOF, right? So carbon would be 1s2, 2s2, 2p2. N would be 1s2, 2s2, 2p3, and so forth. And you can go all the way through the whole chart like that. And we're not going to do that because it's just kind of like an exercise that is not something we need to really spend a lot of time on. The other thing I'll say about it before we move on is that those twos and ones and twos that we mentioned for the number of electrons that are in these particular subshells are written as superscripts. So it would be like 1s2 would be written 1s superscript 2. Degenerate orbitals would be like the p orbitals, where you have 3 p orbitals that all have the same energy. So even though they're denoted like px, py, and pz, they're all the same energy. So that's called degenerate, which you'll probably never see that again, even on a test. Okay, the next two you'll want to remember, the ground state configuration is the lowest energy state that's available to an atom. In other words, if all the electrons in an atom are going in exactly down, all the way down to the lowest energy state that's available to them, that's called the ground state. So, I mean, if it's at that level, then they can't get any lower, but they can get higher. So if you bump them with another atom, for example, then it could excite some of those electrons to move up to higher levels, as we've talked about before. But they won't stay up in those higher levels. As we mentioned before, also, they'll eventually drop back down to the ground state. And then this last definition, the Aufbau principle, is from the German Aufbauen, which just means to build up. Bauen is to build. So Aufbauen is to build up. They do their words slightly differently. And this is just the way that we've been talking about how to determine which way these orbitals, like 1s2, 2s2, 2p6, and so forth, how they're going to fill up. That's the Aufbau principle. So it's just a way of determining how these things are going to fill. Next. So the Aufbau principle has a couple of rules. Lower energy filled before higher energy, that's obvious, right? So we already knew that. And then we already knew number 2, an orbital can only hold 2 electrons, and those 2 electrons will have to have opposite spins. That way the 4 quantum numbers won't be the same. So if one of them is plus 1/2, the other one has to be the opposite, has to be minus 1/2. We're talking about the 4th quantum number. If 2 or more degenerate, remember that means they're the same energy, orbitals are available. Like if you have px, py, and pz, which rather than to write px, py, and pz, I'm just going to draw 3 lines to represent one is px, one is py, and one is pz. What Hund's rule is saying is that, for example, if you're going to start to fill these orbitals, the way they fill is not like you put one in here, spin up, and then put another one over here, spin down next to it. The way they'll actually fill is that they'll go in, spin up, and spin up until all the orbitals are half full. And then you come back over here and start over again, and you put in spin down. Every time you go to another element, another proton, another electron, then you put them in that way. So the reason that happens is because when you're putting these electrons into these orbitals, they're going to try to spread out as much as they can. So they're not going to go in like spin up and spin down in just this first orbital, because that will put both of them right next to each other. Whereas if you put them in the way that I said before, they'll spread out more. So that is referred to as Hund's rule, and you will see this on probably your test in the semester and the final. Next slide. So this is just an explanation of what we just said. So you can pause and read this. Next slide. And this is a picture showing the different breakups of the different regions for the chart. So it can be divided into 4 regions this way. So 1, 2, 3, and 4. And we've talked about this before. The blocks are listed at the bottom if you want to look at that. Next. All right, so this is what we were talking about the configurations, and this is the part I'm going to have to just skip and let you do this on your own, because you can do this on your own, and we're out of time, actually over like 10 minutes over already. So electronic configuration for H would be 1s2, because you've got 1 electron in the 1s subshell. So the electrons would be the numbers here at the top, the superscripts, and then this 1s refers to the fact that you're in the first row and you're in the s suborbital of the first row, which means for the first row there's only 1. Let's skip over, I'm just going to start skipping. So next, we've already talked about helium. So the difference would be that for helium, you would have 2 electrons in the 1s suborbital. First row, s suborbital. When you get to the second row, though, you can not only have s's, so you could have 2 s, but remember we also could have 2 p's. So that would be for boron, carbon, nitrogen, oxygen, fluorine, and neon. So you can also have 2 p's over here. So you could have up to 2s1, 2s2, and then you could have 2p1, which would be boron, 2p2, which is carbon, 2p3 would be nitrogen. So I'll just write that. So 2p3, you have 3 electrons in the 2p shell, then you've got yourself a nitrogen. 2p4 would be oxygen, 2p5 would be fluorine, and so forth. So next slide. All right, so there's a whole bunch of these, so I'm just going to go ahead and skip through these kind of quickly. I'll leave them up for just a moment, so if you want to pause, you can. So next, 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 next. And then you occasionally will have a situation where, for example, here, for chromium, you would expect it to be argon 4s2 3d4, and it actually doesn't do that. It actually makes argon and 3d5 here, and then 4s1. And the reason it does that is because when orbitals are half full, they're relatively stable. Which is because, for example, for the D's, if every one of them is half full, let me just draw this real quickly, even though we're out of time. D's have 5 orbitals. Remember we drew the P's before, like about maybe 4 or 5 minutes ago. We drew 3 of them because P's have 3 orbitals, and we drew the arrows up, up, up first, and then down, down, down. So for D's, you do the same thing. That's Hund's rule. So, but for D's, you have 5. So when you put them in, you want them to spread out as much as possible. So you put in spin up, spin up, spin up, spin up, spin up, until all of them are half full. And so this configuration here, when they're all half full, is somewhat stable because all of these have 1 electron in them. It would be more stable if they all had 2, and then you would have a full subshell of D's. But when it's like this, it has a certain amount of stability, so it will actually not exist like this. It will actually flip over, kind of like in resonance, when we talk about resonance later. It will flip over to this configuration because it's more stable. In other words, it's lower in energy. And then the same thing can happen down here. Sorry, I don't know why I said arsenic, for copper. Okay, next slide. So here's our chart again, next slide. So write the ground state configuration for francium. So I would go back to that chart if I could, but I can't. So let's go to the next slide. So if you have your chart, or if you can get to a chart, just look francium up. It's in the first column or group, and it's all the way at the bottom. The atomic number is 87. So to write it out the long way, this is what you have to write. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and so forth, all the way over here until you get to the 7th row, or period. And then there's 1 electron in the 7s area, because you're in the, like in the chart, you're in the first column in the chart. So you're in this column right here, all the way down here at the bottom. So there's francium. In fact, I don't think all charts even have it on there. Some of the abbreviated charts may not even have it on there. But it's all the way at the bottom left. So you can write it this way and it's perfectly legitimate, but it just takes kind of a long time. So there's a shortcut way you can do it where you don't have to do all of this. You can just write radon in brackets and then write 7s1. Just write that last part, because when you're writing the radon in brackets, what you're saying is that it has the same configuration as radon plus the 7s1, where radon would be on the other side of the chart in the previous row right there. So it would be one row up all the way over. Have to make that crooked to get it right, but so it would be one row up at the very end on the right hand side in the 8th column. So this would be radon. Excuse me. So the francium would have the same configuration as the radon, but just with one more electron, which would happen to be in the 7 row S subshell area over here. So first 2 columns are S's, and then we would be in the 7th row here. So radon would be in the 6th row. So we have the same thing that radon has as far as the electronic configuration, plus 1 electron in the 7s subshell. Okay, so next slide. So what we were just talking about, here's the radon, and then here's the francium. Okay, next slide. And then this is just another chart that shows the different subshells on the chart, showing that the chart's basically designed around these subshells. Next slide. And then here is another slide that is showing you that things tend to take octet configurations. So what will tend to happen, next slide, well, they didn't list it, so we'll come back to that in the next chapter, in chapter 7, when we talk about periodicity. But things in the first column have 1 valence electron, which they typically will get rid of in order to attain an octet configuration, and things in the 7th column tend to gain 1, and we've also talked about this before. So let's stop, because we're already at an hour and 45 minutes, which is way too long. So I'm going to go ahead and cut it short, and I'll see you in the chapter 6 work problems.